All right, well, welcome to what we're going to call the colligative properties of solutions. And these are terms that you've heard before because last year in honors chemistry we did what's called boiling point elevation and freezing point depression. And what colligative properties mean is this. We have a solution that is, for example, say, a pure liquid, and colligative properties mean how do these solutions change from the pure solvent. And if we were to suddenly add a bunch of solute particles to this pure liquid, they don't do anything but get in the way. So it means that they prevent this pure liquid from going from the liquid to the gas phase. It means that not only do they elevate boiling point because you have to heat them more to get them to leave the liquid phase, not only do they lower the freezing point because you have to lower the temperature more to get them to actually create that interface that goes from a liquid to solid. They also lower the standard vapor pressure. So if a substance is just sitting here on the surface, on the table, evaporating into a closed space, we would have a measurable vapor pressure. But you start adding all of these solute particles and it lowers vapor pressure. So all of these properties, they all depend on concentration. And in terms of the boiling point elevation and freezing point depression, we measure that concentration in molality. But we're going to be looking at something called osmotic pressure, which is going to measure in molality. Let's not worry so much about the osmotic pressure yet. We'll come to that. Let's do a quick review and let's take a look at a boiling point elevation problem. And we'll do one with an electrolyte. So here's a question you could expect to ask. What is the new boiling point of a 12 molal solution of sodium chloride? Remember that the equation for calculating delta TB, the change in boiling point, is equal to KB times molality times I. Let's remember that this KB is the boiling point constant. And it is a constant for a different solvent every time. For water, the KB is 0.51 degrees Celsius per molal. Obviously, this thing called M is molality. We know that. We've seen this before. And let's remember that this crazy little dude over here is what we call the Van't Hoff factor. And it is a multiplier by how a substance dissociates. So if sodium chloride dissociates into sodium and chlorine, then 1 mole of sodium chloride would give us 1 mole of sodium and 1 mole of chloride ions for a total of actually 2 moles. So this would have a Van't Hoff factor of 2 because it's has twice the effect of the actual concentration of the solute involved. And remember that this is only useful for electrolytes. So let's try this. Let's calculate this. If we know that the KB for water is 0.51 degrees Celsius per molal, we know we have a molality of 12 and we have a Van't Hoff factor of 2. Let's calculate our delta TB. You have a calculator, I hope. 0.51 times 12 times 2. And I get a delta TB of 12.24 degrees Celsius. But let's remember that this is only the change. This is not the new boiling point. So we want to be careful. If the original boiling point for water is 100 degrees Celsius, and we have changed the boiling point by 12.24 degrees Celsius, then our new boiling point is going to be 112.24 degrees Celsius. Okay, we've seen that before. Let's take a look at something new. This is called osmotic pressure. We're going to represent this osmotic pressure by the uppercase letter pi. So don't freak out when you see that. Okay, it's a Greek letter, and you've used the lowercase one ever since you were in junior high for the radius of a circle's circumference. Sorry, the ratio of a circle's circumference to radius. So you've seen that before. This is our osmotic pressure, and this is what we mean by osmotic pressure. If we were to take, say, for example, this is kind of a weird drawing, but it's better than me trying to draw it. Check out what happens. Let's say that we have this situation where we've got a solvent. It can be anything. Usually it's water, H2O. And we've got this osmotic pressure measuring manifold. And what we have is a semi-permeable membrane here that only allows water and doesn't allow solute to go through it. And water has this osmotic tendency to want to flow to areas of a greater concentration of ions to equilibrate the concentration. That means that if there is no solute particles on this side and a bunch of them on this side, water has a tendency to want to equilibrate the concentration. That means water is going to want to osmotically flow towards the area of high concentration from low concentration. Obviously, this is called osmotic pressure because water is exerting a pressure on this membrane due to its tendency to want to flow this way. And of course, if we let it happen, then we would see that the level of water on this side would drop because it's all going this way. Remember that this is a semi-permeable membrane, and so the water is actually going to drive up the level on the other side. And this is what's called osmotic pressure. We're going to call that pi, the capital pi, and it's measured in atmospheres. Well, just like all colligative properties, the greater the concentration, the greater the effect is. And so the equation for osmotic pressure pi is equal to mRT, where this M is molarity. This guy R is our old buddy, the gas constant R, 0.0821 liter atmospheres over moles Kelvin. And this T, of course, is our temperature in kelvins. Let's try one. Okay, here's one. What's the osmotic pressure of 50 grams of calcium chloride? It's an electrolyte with a Van Hoff factor of 3 and 500 mils of water at 25 degrees Celsius. So the first thing we want to do is find out how many moles of CaCl2 we have. If we have 50 grams of CaCl2, and depending on how you round chlorine, you should get a molar mass of either 110 or 112, because there are 2 chlorines plus our 40 grams of calcium. So I usually round chlorine to 36, but you can do it however you want. So how many moles are we talking about of calcium chloride if we only have 50 grams? And this is, of course, 0.446. Let's call it 0.45 moles. All right. So if we know we have 0.45 moles, what's our molarity? Molarity is equal to moles over liters. We have 0.45 moles of calcium chloride. We are in 500 milliliters, otherwise known as 0.5 liters. And we should get a molarity of 0.9 molar. All right, let's plug this into our equation. According to this equation for osmotic pressure in atmospheres is equal to molarity times the ideal gas constant times the temperature in kelvins. So we have a molarity, 0.9 moles per liter. I'm going to write out the molarity like this. Our ideal gas constant, 0.0821 liter atmospheres over Kelvin moles. And our temperature is 25 degrees Celsius. We're going to add 273 to that to get it into kelvins. Now check out what happens to the units. Kelvins cancels kelvins. Liters cancels liters. Moles cancels moles. It leaves our answer in atmospheres, but we're forgetting one thing. This is an electrolyte. So we want to include the Van Hoff factor. And so we'll multiply this whole thing by 3. So let's crank this out. What's our osmotic pressure? 0.9 times 0.0821 times 298 kelvins times 3 is an osmotic pressure of 66 atmospheres. Okay, and that's all you do. And so I will see you guys all on the next one.